Thank you everyone for coming to this session. My name is Yuhao Yang, and I'm a senior software engineer from Intel Data Analytics team. Together with me is Bala. He's from the Dell Technologies, and he's also a senior technical software engineer. Today is a great opportunity to share some of the work that we did on distributed deep learning applications. So there are two parts of my job. First is that at Intel, we developed some deep learning libraries on Apache Spark, which are specialized to help people to run distributed TensorFlow, Keras, and BigDL applications. And the second part is to help Intel partners and customers to use those libraries and develop the deep learning applications according to their requirements. So today's agenda, we'll start by defining our problem. Basically, we trained a model using Spark ML pipeline and Analytics Zoo to detect diseases from the X-ray images. And next, I will give a general introduction of Analytics Zoo, and then Bala will take over to give you a detailed introduction to our chest X-ray model and our results. So our problem is a quite straightforward one. So given the X-ray images, we want to detect if there's a disease in, that a radiologist, a trained radiologist can tell from that image. And we want to train a deep learning model that can mimic the knowledge, that can copy the knowledge of the radiologist and then automatically detect the diseases hidden in this image. And there are actually, for different user groups, Analytics Zoo is providing different API. And for this project, we use the API of Spark ML pipeline. Here, the ML pipeline refers to the pipeline defined in the Spark ML components, where users can use estimators and transformers to compose a pipeline and call fit and get a pipeline model. So it's a more integrated way to help people to connect the data ingestion, feature engineering, and the model training and evaluation. And next, we are going to demo some of the feature engineering steps that we have in Analytics Zoo and how it can be used in a transfer learning application. And next, we are going to demo how the how the model scales during the training and inference. And the CHX-NIGHT model, this is not a new problem. And the researchers from Stanford University actually developed this model called CHX-NIGHT, which is already the state of the art for this problem, and is already exceeding the normal trained radiologist on the precision for detecting those diseases. So our training data is from this public data site. It's available from Kaggle, so everyone feel free to download the data. And for this model and the project is open source, and we are providing notebooks at the end. So feel free to download the notebook and data and try by yourself. And in this data set, there's over 100,000 images from over 30K different patients. So there could be multiple images for one patient, taken from different angles, some from front, some from back, and some from sideways, and taken at different times. And for each of the images, there are multi-labels attached to it. So for example, I listed a few records here. So for the 13th patient, we have 4 images for them. And from each of the images, we have labels that are labeled by the human radiologists. And like for the first image, a radiologist can tell 4 diseases from it, 3 diseases from it. And from the last image, 008, a radiologist cannot find anything from it. And on the right corner, we listed the counts of different diseases in this data set. And about half of the images in this data set suggest nothing. So half of the images in this data set actually are healthy images, at least from that X-ray image. And the distribution for different diseases are quite different. So the most popular one is the infiltration, and it got over 20K positive instances in the whole data set. However, hernia only got about 200 positive instances. So again, each of the record can have multiple labels attached to it. So we are trying to train a multiple label model for resolving this problem. That means we train a single model that can predict those 14 diseases together at one time. Okay, so little more knowledge about Analytics Zoo. So Analytics Zoo is an open source deep learning library that's primarily developed at Intel, but now it's going to the public, and we are accepting contributions from a lot of other companies like Ali and Tencent. And it's a distributed TensorFlow, Keras, and BigDL platform, totally built on Apache Spark, and we made a lot of specific optimization to make the parameter synchronization and multi-threading more optimized for the Spark platform. And inside the Analytics Zoo, we provide a lot of reference use cases. Each of the use cases represent one typical scenario in some industry, and all of them are end-to-end examples, including the data ingestion, feature engineering, model training, and evaluation. All of them are trained on public data set, so if you're interested in a particular one, feel free to download and try the notebook. And the second part, we include we have a lot of pre-trained models in the Analytics Zoo. And for image classification, we provide over 20 most popular deep learning models like Inception, ResNet, VGG, or even DenseNet and MobileNet. And for object detection, we provide some public data set, models trained on the public data set, including YOLO V2 and FastRCN. And next to that, we have feature engineering, since Analytics Zoo is designed to provide an end-to-end solution. So we are providing a lot of components to help people to ingest their data from the raw format. And from high-level APIs, we provide different APIs for different user groups. For data scientists, we provide TensorFlow and Keras APIs. So that means people can combine their TensorFlow API with Analytics Zoo API. So with some minor changes from their TensorFlow code, they can parallelize their data into a Spark RDD and then feed the data into an optimizer of the TensorFlow. So basically, TensorFlow users should be able to reuse the models and loss functions that they defined using TensorFlow API. And Analytics Zoo will pick up the model they defined and run it distributedly on Spark platform. We have related talks on that, and also feel free to check the documentation for examples on that. And for Keras, we actually implemented our own Keras wrappers for for people to run deep learning applications on Spark. And so basically, Keras users, they just need to change the namespace of their code, and they can adapt their Keras applications to Spark. And for Spark users, we also provide the ML pipeline and DataFrame integration. So we can provide estimator and transformer interface, so people can pick up, most times it's for users that already have a deep learning model in their Spark ML lab model in their system, and now they want to try with deep learning models. So they can just use the same data frame, but apply a deep learning model to it. And in this use case, we are using the Spark ML pipeline and data frame pattern. And you can see how we load the images and do transformation and do the model training in Spark data frame. So in the back end, we have Spark, TensorFlow, and Keras, and BigDL. Okay, for BigDL, it's the first deep learning library that's released by Intel, and it's providing a lot of fundamental components for building a distributed deep learning application on Spark. So Analytics Zoo internally use some of the mechanism provided by BigDL, like parameter synchronization and threading, and a lot of the BLAS operation in Analytics Zoo are actually conducted by the Intel MKL that's embedded in Intel BigDL. So BigDL itself and Analytics Zoo, we are trying to help Spark users to pick up those frameworks really easily. And one headache they often have is that they cannot change the production environment to just apply a new framework. So to address that problem, we build our package as a standard Spark program. So that means you don't really need to change anything on your production cluster to run a BigDL program or an Analytics Zoo program. For Java or Scala programmers, BigDL and Analytics Zoo are just jar files that you can refer to. And just like a normal Spark job, you can just submit the jar file together with your application to a Spark cluster. So that means no change is required. And for Python users, we provide a virtual environment, so you don't even to install any TensorFlow or other libraries on your Spark workers. And BigDL also provides high performance on CPU is because we have the built-in support from Intel MKL. And the Intel MKL is also built into the BigDL library, so you don't really need to install MKL on any of your workers or Spark nodes. And it's natively providing the scaling out from Spark. And internally, we just use the synchronized mini batch for the model training. So it's a typical way for running a Spark training job. So the driver will submit its job to the cluster, and each of the worker will train will have an independent copy of the model. And with that local copy of the model, it will calculate the gradients, and then all the gradients will be aggregated to calculate the final weights. And after this iteration, for the next iteration, the weights will be repopulated to all the workers. So this distributed training iterations happens as standard Spark jobs. But internally, we did a lot of optimization for speed up the parameter synchronization process. We call this all reduce, but basically we avoid the shuffle process introduced usually by Spark aggregation process. So each of the worker, each of the executor in a BigDL program will actually covers a part of the whole parameter range. So it will try to aggregate all the gradients from other workers for that range of the parameters. And after the aggregation, it will repopulate or broadcast that part of the aggregated gradients to all the other workers. So it's like a P2P process for the parameter synchronization. And by using that mechanism, we avoid the shuffle process. So each of the iteration in a BigDL training process typically is very short. It can be below 1 second also. And for this project, we are using this machine learning, deep learning pipeline system. So all the images are hosted on a HDFS system as the raw images. And we are using an image reader to read the image data, and the results are hosted in an image data frame. And from that point, user can choose, they can just save the data frame into HDFS system again, because for the model tuning process, they need to reload the image data multiple times. And save partition the data frame can, save them some time from reloading the images. And after that, we perform some image pre-processing steps and then send the images for the fitting. And after that, we got a pipeline model that can be directly applied to the raw data. So next, I will hand it over to my partner, Bala, who will give a detailed introduction to our model and a code-level introduction to our project.
Okay. Thank you, Yuha, and good afternoon. So now that we have seen an overview of Analytics Zoo, let's see how we can build a deep neural network to predict diseases in chest X-ray in Spark using the Analytics Zoo API. What I've done is I've broken down the steps in building the model as shown. First, we'll see how we read the images. Then we'll do some feature engineering on the images. Then we'll show how we build the model. Then we will define the optimizer, and then we'll train the model. So in the next few slides, we will go over them in a little bit of detail. OK, so let's read the images. So first, you have to initialize the Spark context. And in this case, you are initializing the neural network context. Then you're using the NN image reader to read the images from your HDFS. When it reads it, it reads it as Spark DataFrames, and you can point it to a folder, and the images can be any standard formats like JPEG, PNG, and so on. So it supports all that. One thing I want to highlight here is you can see the parameters about resizing, right? So the original X-ray images from the National Health Institute are 1024 by 1024. So we are downsizing the images to 256 by 256. So we found in our studies, as well as in Stanford studies, that downsizing the images does not have a significant impact on the performance. So that's the reason we are doing it. One cool thing I want to note here is that when you are reading it and downsizing it, the images are read in a reduced size. So the original images are never saved in the memory. So you are getting some optimizations in memory there. And finally, if you are familiar with OpenCV, the last parameter would make sense. So it's open codec equals 1. So this is as OpenCV integrated into it. This specifies the format in which you read the images. So in this case, we are reading it as RGB. That's how we read the images. And then now the images are as Spark data frames. So any operation you do, any transformations you do, are all Spark transformations. Right? So that's the advantage of having a deep neural network framework in Spark, because all your operations are Spark transformations. OK, so one example is a joint transformation that we have here. So we have read the images. We are also reading the labels as CSV files, and then we are joining them. So I wanted to illustrate that you can do these Spark transformations on your images. OK. So we have read the images. Let's do some feature engineering. So these are the image pre-processing operations we do on the chest X-rays. So I've shown 3 here. So we are doing center crop. We are randomly selecting a few images to adjust the brightness. And then we are randomly selecting a certain percentage of images to flip them horizontally. Why do we do it? Based on our studies and our experiments, we found that doing this improves the accuracy, also the robustness of the model. And as you can see here, all these are, again, Spark transformations now. And finally, the model is still expecting a multidimensional tensor. So that's the last operation. 2tensor converts the images into multidimensional, in this case, 4 dimensions, the width, height, the number of channels, and then the batch of images. So those are the 4 images that we send it to the model. So all of them are combined in the chained pre-processing API that's available in Analytics Zoo. OK, so now we have read the images. We have done some image processing of chest X-rays. So let's go define the model. Before we do that, I want to talk about some transfer learning. If you're familiar with image classification, there are some popular image classification models. And what I have is a convolutional neural network on the slide. So the popular ones are Inception, ResNet, and DenseNet. So Inception was released by Google, ResNet is released by Microsoft, and I think DenseNet is Facebook and Cornell University. So these are, you can think of them as off-the-shelf image classification models. So you don't have to build your own model, you can reuse these. In addition to that, you can use these models that are pre-trained by some example. In this case, these models are pre-trained by ImageNet. ImageNet is again an open source data images. So there are like 15 million images, thousands of categories. So these models are trained with ImageNet. So if you don't use transfer learning, your weights are all random, right? But when you're using transfer learning, you are taking a pre-trained model and you are starting at a much different level. So your model will converge faster. And that's what you're doing. We are using transfer learning to train the X-rays. However, when you're doing transfer learning, you have to do a few things. So you have to add an input layer. So for your problem, so you have to add an input layer for X-rays. You have to take the classification layer for the original problem, the ImageNet. You have to remove that and add a new classification layer for your problem. So you have to do these things, and that's what the figure illustrates. So we can see we're adding a new classification layer for the chest X-rays, and you can see the diseases and the probability of them that are shown by the node. OK, so this is what transfer learning is. So let's see how we have implemented it. First, so we go load the pre-trained model using net.load API. And then we remove the classification layer from the original problem, which is ResNet with ImageNet. And so we remove the final softmax classification layer. We add a new layer for X-rays, and then we add a new classification layer. And we use the activation function as sigmoid. So our problem in chest X-rays, there are 14 diseases, right? And these are multi-class and multi-label, meaning each X-ray can have multiple diseases. So that's why we are using a sigmoid function, because in the final classification layer, you'll have 14 output nodes, and each has to give a probability whether that disease is there or not in the X-ray, independent of the others. So that's why we are using a sigmoid activation function. And finally, to avoid overfitting, we are using regularization and dropouts. OK, so we have read the images. We have done some feature engineering. We have defined the model. Actually, so here's the code that explains how the model is defined. So we are using the APIs to load the image. We are removing the final layer, adding a new layer, and so on. One thing I want to highlight here is we are using the global average pooling 2D. So the final layer is multidimensional, so we are flattening it using that. We could have used a dense layer, but we found that global average pooling 2D actually improves our performance and significantly reduces the computation. And then finally, we are using dropout and regularization, as we discussed before. OK, now that we have defined the model, let's go define the optimizer. So we have evaluated two optimizers, SGD and Adam. And in the results, we'll see how and why. In addition to that, we have done learning rate scheduler. So what it does is it adaptively changes the learning rate based on how our model trains. So we have done it in two phases. One, a warm-up phase, where we gradually increase the learning rate to speed up the learning of the model. Then there's the second phase called plateau, where we hold what the learning rate is and decrease it if the model starts to train and the loss function starts to even out. So that's the warm-up and plateau. And let me spend a little bit of time explaining the plateau API. So in this case, we are monitoring the loss function. We are making sure, so if the loss function changes, we are reducing it. We are reducing the learning rate by a factor of 0.1. The patience represents the number of epochs we are monitoring the loss function. Mode is min, meaning we are trying to wait for the loss function to reduce. Epsilon is the delta for the loss function. So we are basically looking at the loss function and making sure if it doesn't go below the epsilon, which is 0.01, and that's when we will reduce the learning rate by the factor. Cooldown is how many epochs we wait before we change it, and here in this case is 0, and minimum learning rate is 1 e power minus 15. Again, to simplify this, we are monitoring the loss function, and if that doesn't reduce, we will start reducing the learning rate so our model converges. So that's the gist of it. Okay, so that's our optimizer. Okay, so now we have read the images, done feature engineering, model, optimizer, everything is defined. Let's go train the model. Now, if you have used ML pipelines, this would immediately click, and I don't even have to explain what's going on. To simply put, we have an estimator to build a model. So if you use ML pipelines, it's estimators, right? You do dot fit to train the model, and that gives you a neural network, which is nothing but a transformer. So if you remember in ML pipelines, you do a dot fit, you get a machine learning model, and then that's again an ML transformer. So in this case, you can also do dot predict and for inference. On a side note, you have already mentioned this, and then I wanted to reinforce this. Because the way we have developed Analytics Zoo, it is very close to the ML pipelines. So let's say you're building a recommendation system, right? And that would have an ensemble of models, right? You have some machine learning models, and then you have some deep learning pipelines, right? So for machine learning models, you can use their ML pipelines. For deep learning, you can use Analytics Zoo. So you can have all of those combined into one integrated single pipeline. So for machine learning, you can use ML pipelines. For deep learning, you will use Analytics Zoo. So that's why having Analytics Zoo natively built in Spark would be very advantageous to you. Okay, so now back to this. So we are using, like I said, NN estimator to build a model, and dot fit trains it. We are using AUC ROC to measure the accuracy of the model. And then we are using, again, ML pipeline API binary classification evaluator to determine the AUC ROC. Again, this shows how integrated Analytics Zoo is to ML pipelines, if you're familiar with ML pipelines. So you can use some of its capabilities in your model. Okay. And then in the code snippet, it basically explains what's there in the text, and briefly cover it. So we have the X-ray model, which is what we defined 2 steps before. We use binary cross entropy. That's the loss function. We use the transformer, which is what the feature engineering is, if you remember the chain pre-processing. And then we set the batch, max epoch, and other parameters to train the model. And then finally, the optimizer is the optimizer that we defined earlier. So all that are put together to your model. And then you do dot fit, and that's when you train the model. Okay? So you saw how we developed the model. You saw all the steps, and then how we trained it. So let's go look at the results and some of the observations. Before jumping into it, I want to give some brief recommendations on what we learned from Spark and what kind of Spark parameters we use. So for number of executors, we used it as the number of compute nodes. Number of executor cores is the number of cores that are available in the node, physical cores. And then we left 2 cores for any additional overhead. Executor memory, so that's what is a little bit tricky. So if you remember the earlier slide that you have showed where you have distributed training, each core has a task, and each task has its own neural network, and then a batch of images that it's working on. So for each core, you have to allocate memory for the network as well as for the data partition, and then you multiply that by the number of cores in that executor. So that's what this slide shows. So the executor memory is the number of cores in the memory, and then for each core, you calculate how much memory that's needed. So in our case, we are using like 300 gigs of memory for ResNet. Okay, so now let's look at some of the results. So first, let's see how the learning rate scheduler impacts our training. As I said, we use SGD and Atom Optimizer, and Atom Optimizer outputs SGD. I haven't even plotted SGD here because it's trains very slowly. For Atom Optimizer, you're seeing 3 lines here. The blue line is the learning rate scheduler, and the orange line is how our model trains with learning rate scheduler, and the gray is how our model trains without the learning rate scheduler. So you can see without the learning rate scheduler, it's very slow learning. But with learning rate scheduler, where you have a warm-up and then a plateau, our model trains quickly. And in 15 epochs, we achieve around 80% average accuracy. Okay? So these are the results. So these are, on the x-axis, you see all the 14 diseases. On the y-axis, we are using AUC. And you can see, you can focus on the orange one because that's the ResNet model. That's what we wanted to highlight. And you can see how that performs for each of the diseases. For some disease like edema, you can see that we are getting like close to 90% accuracy. For others, it's 70–80%. The average is 80. I think this beats even some of human inference of just X-rays in some cases. I also wanted to highlight Inception and DenseNet. Inception trains much faster because it's a smaller model and it's an earlier version, but it's not performs as well as the ResNet. Whereas DenseNet takes up too much time and it's still not as good as ResNet. Also, ResNet scales better, and which is what you'll see in the following slides. Okay, before we see how our model scales in Apache Spark, I just wanted to spend some time on batch size. And that's pretty important for scalability. So for batch size, there are 2 things. One, batches per thread, which is, you can imagine as how much work does an individual thread does. And then you multiply that with the number of workers, so that's your global batch size. So if you plot the accuracy with batch size, you get a graph like this. So for lower batches, you get very low performance, and then it kind of increases, and it stays there, but then it slowly drops down. Now, the reason why it drops down could really depend on your model or your use case, right? So this pattern is true across most use cases, not just for image processing or just X-rays, right? And the reason why it drops down is important because you have to increase your batch size if you want to scale. And if you're increasing your batch size and if your model is performing not so good, then you have problems with scalability, right? So, and that's where you can't just scale your model. You'd have to go tune other things, like you have to come up with a different optimizer and so on. So that's pretty important to note. So batch size is important. Increasing batch size increases your scalability, but increasing the batch size may not always have the same results. Your accuracy may go down. But in our case, we did scalability from 4 to 16 nodes, 4, 8, 12, and 16. We increased the batch sizes as we scaled, and we didn't see any loss in performance. We got 3 times the speed up going from 4 to 16 nodes. So in a 16-node Apache Spark cluster, you can train our model in 2.5 hours to predict diseases in chest X-ray, which is pretty good if you consider what it's doing. Okay. So that's how we saw scalability. Now, how does it scale beyond this is something we want to do in the future, because as it scales, we may not see the accuracy. We may see the accuracy may be going down, so we'd have to investigate other parameters, and that's what we are going to implement. We have to implement LAS and other advanced capabilities to see we can scale to hundreds of nodes and see how the model performs. We want to also do some additional features. I believe the NIH X-rays have patient information such as gender, age, and other things, so we want to incorporate them and see. One of the things that was most challenging to me, and anybody who worked on Spark will understand that it's very difficult to predict why your nodes are failing, why our executors are failing. It's very difficult to size your memory and things like that. So that's another thing we want to focus. How do we come up with performance characterization for these different workloads? How do we size them? How do we provide better guidance for your problem? all this code is available on GitHub. So you can go download that. So the dataset is available as open source in Kaggle and NIH. The code is available, so you can go and download it and try this for ourselves. So I wanted to acknowledge a few people who helped in this project, and thank you all for coming. I know you had 13 other sessions that you could have chosen, but so I really appreciate you attending this session. Please provide feedback, and I'll take questions. Thank you. Any questions? Cool.
You probably mentioned this, but what is the distribution strategy for your neural net if you're doing a distributed training?
What do you mean by distributed strategy?
Are you using a parameter server or are you using Horowat?
Sure. So all that, because Analytics Zoo is built natively in Spark, we don't have to worry about that. Analytics Zoo takes care of that in the back end. And the way that works is how you have explained here. And I think you can explain it better than me, how.
Do you want to take this?
Okay, yeah, it's working now.
The parameter synchronization is a critical part for any distributed deep learning applications, and we did throw a lot of effort on optimizing that. And it's actually built in BigDL, so each of the worker will cover a part of the whole parameter range. And during each of the iteration, other worker will send the gradients of that part to that worker. So that worker will have the final updates on the weight. And after aggregating all the gradients, it will calculate the weight for that part, and it will repopulate that part of the weights to other workers. So in the end, all the workers get the final updated weights for the whole iteration. So that's how we use the block manager in Spark to do the parameter synchronization. In a way, we managed to create a parameter server based on the mechanism provided within Spark. So we also, there's a detailed introduction for this part in the white paper of BigDL and Analytics Zoo, and we have a previous Spark session about it.
Just one more question. What is the output model format? Is it a Spark model or?
Okay, for the trained model, you can export it into multiple formats, including TensorFlow, Keras, and BigDL format. For BigDL, we use protobuffer to save the metadata, and then just the binaries for the weights. It's a BigDL format, but again, you can export it to other format as well.
Could you go back to the slide that shows the performance benchmark?
Sure. Okay, I'll do it here. This guy?
No, I don't see it.
Oh, it's not showing. Oh, sorry. Hang on. Okay, there you go.
Okay, so these numbers are when you ran your application, right? With
yes.
different starting point, right? So these three were kind of, you trained your model using each of these, and these are the numbers?
Right.
Have you also tried training it? Let's say if I trained use same thing, but instead of using Analytics Zoo, have you tried just doing a pure TensorFlow, and what would the numbers look like?
So we did only Analytics Zoo because that's what this study is based on. The Stanford University, they did it in TensorFlow, and I think they used DenseNet, and they didn't scale, right? So that was on a specific node. So and that's state-of-the-art research. We are just trying to replace that. So in their case, so our best results are 2% lower than Stanford University. That's what we found.
Okay, and so when you say scale, like what's the time difference between, so since Stanford didn't use distributed, right? I assume they did on single node. How much was the time difference to train the same model?
So you mean difference between like a 4 node to 16 nodes, or difference between this and a
non-distributed,
Spark.
like the state-of-the-art that Stanford did.
We haven't compared that. And so a couple of reasons, right? Because we are using Spark here. So Spark itself would have a overhead. So I think the point of this exercise is to show that if you are using Spark, and if you have your data in Spark, you can build these things natively in Spark instead of going and looking at something
Right,
else.
but I guess what I'm trying to figure out, is there a benefit of using Spark for that? Like, am I saving a lot of time, or is
Well,
it just something else?
I think Spark itself has some overhead, but the benefit is not time if you look at Spark, right?
Okay.
So you get additional benefits. So it massively scales. It has RDDs into it. So those are the benefits of Spark rather than, hey, I'm going to get better performance and better scalability. Right.
Okay, thank you.
Somebody had a question here. I think that person left probably. Any other questions? Cool, thanks a lot. Bye.